Okay. Now students, down you see how to get the state space model when the differential equation is given, transfer function is given, block diagram is given, signal flow graph is given, circuit is given. Am I right? Now we will see once if you find the state space model, but in the GATE examination state space model is not given. He is not giving state equation, output equation directly. You find state equation, output equation, he may give the differential equation, transfer function, block diagram, signal flow graph like that. Okay. So, sir, then what is the state space analysis? The state space analysis is nothing but once if you get the model, means once you get the A, B, C matrices, you can easily find the questions. Okay. Now that question and answers is nothing but the state space analysis. Okay. So now we'll see what is the state space analysis questions. Now if that question is coming, how to solve. Okay. So I can explain each and everything one by one. So now the first one I want to explain state space model transfer function. What is the first question? A question or whatever it may. Okay. State space model transfer function. Now first of all, you tell me what is the state equation. Now this is the state equation dx of t by dt, which is equal to a into x of t plus b into u of t. This is the state equation, right? Now first you find the transfer function, means first I want to apply Laplace transformation. What is Laplace transformation? Apply Laplace transformation. Laplace transformation is s into x of s, which is equal to a into x of s plus b into u of s. Then you take x of s as a common. So if you take x of s as a common, s minus a, but a is not a constant, a is a matrix. Therefore this s is multiplied with identity matrix. Then this identity matrix order is same as that of a matrix, which is equal to b into u of s. Therefore what is x of s? X of s, which is nothing but si minus a matrix inverse into b into u of s. Si minus a matrix is go to that side, inverse si minus a matrix inverse into b into u of s. Now this is the state equation, but I want a state space model transfer function. Transfer function means output equation. What is output equation? Y of t, which is equal to c into x of t plus d into u of t. This is the output equation. Then you apply the Laplace transformation. Then if you apply Laplace transformation, then this is the Laplace transformation, which means that y of s, which is equal to c into x of s plus d into u of s. Therefore y of s, which is equal to c into x of s. Just now we find x of s here. Substitute that x of s here. Now this is x of s is nothing but si minus matrix inverse into b into u of s plus d into u of s. Now what is the transfer function? Now the state space model transfer function, state space model transfer function, Laplace transformation of output by Laplace transformation of input, which is nothing but c into si minus a matrix inverse into b plus d. Now this is the state space model transfer function, output by input, which is equal to c into si minus a matrix inverse into b plus d. Now this is the state space model transfer function, output by input. Okay, or you may write like this: c into what is matrix inverse? The matrix inverse is nothing but adjoint of si minus a matrix, adjoint of si minus a matrix by determinant of si minus a matrix into b plus d. So now this is the state space model transfer function, output by input, which is nothing but c into, take LCM, adjoint of si minus a matrix into b plus d into determinant of si minus a by determinant of si minus a. This is the state space model transfer function. This is the state space model transfer function, which is Laplace transformation of output by Laplace transformation of input. So generally the D matrix is not available, then remove this part and C into adjoint of Si minus A into B by determinant of Si minus A. This is the one question may be asking. One question is state space model. Question number 1 is state space model from the differential equation. Now from the state space model, so you can get a state space model from the differential equation. You can get A and B and C matrices. From A, B, C matrices and linked answer question B bit may be asked transfer function. Means if you want to solve transfer function, you require C matrix, you require A matrix, you require B matrix, you have a D matrix, you can take it, otherwise remove this part. Okay. So this is the state space model transfer function, which is determinant of adjoint of A, B, C are involved to find the transfer function. Okay, note down this. Okay. Now this is the state space model transfer function. So sometimes he is asked in the linked question, what is the state space model transfer function? So use ABC matrices and find the transfer function. Now from here I can find one more thing also. Now if you just recollect your closed loop control system, the denominator polynomial of a closed loop control system is called as characteristic equation. The roots of characteristic equation is called as closed loop poles. From the closed loop poles, we will decide the stability of closed loop control system. Denominator polynomial is called as characteristic equation. Roots of characteristic equation is closed loop poles. From the closed loop poles, we will do the closed loop control system stability and behavior and everything. Now similarly, this is similar to a closed loop control system. Now see here, this is the state space model transfer function. Now what is the characteristic equation? What is the characteristic equation of a state space model? The characteristic equation of a state space, the denominator polynomial, the characteristic equation of a state space model is determinant of Si minus A equal to 0. So the roots of characteristic equation, roots of characteristic equation of a state space model is called as eigenvalues. Now which is similar to closed loop poles. Therefore from these eigenvalues we can find closed loop control, from these eigenvalues we can find stability of state space model. From the eigenvalues we can find the stability of state space model. Okay, so stability of the state space model means we require eigenvalues. Eigenvalues, if you want to find, you require A matrix. Okay, therefore now with this particular thing we can what we can identify? He may ask the questions of state space model transfer function, or he may ask eigenvalues, or he may ask stability of a state space model. These three questions are covered with this particular derivation part. Understand not? Now he may ask the state space model transfer function, or he may ask the eigenvalues, or he may ask the stability of the state space model. Then one thing we will do, okay? To cover all these three questions, we will solve one single problem, okay? Such that you can understand how to find the transfer function and how to find the eigenvalues and everything, okay? So provided this transfer function and everything is calculated, provided you have a B, C matrices. But students, remember, in the GATE examination, model is not given 90% not given directly. He is giving differential equation, transfer function, block diagram, signal flow graph, electrical circuit, like that. From that you can find model A, B, C matrices. Okay, note on this. Now I will solve one question such that it will cover these three questions. Okay. Now this is the question number 1. Okay. Now this is the question number 1. What is the question number 1? Now, from the given state space model, this is the model which is given to x1 dot, but he is not giving directly like this. Okay, you want to find -2, -3, 4, -2, x1 x2 plus 3, 5 into u, and y equal to 1, 1 into x1, x2. So what he is given? He is giving state equation and he is giving output equation to you, right? Now he is giving the state equation and he is giving the output equation, means now you have a matrix, B matrix, C matrix. Then what is the question? Now he is asking these three. Find state space model transfer function, find eigenvalues, find the stability of the state space model. Understand not? State space model transfer function, eigenvalues, stability of the state space model. Okay, right. Now, what is the state space model transfer function? The state space model transfer function is nothing but, now the transfer function y of s by u of s, which is equal to c into a joint of si minus a into b plus d. D is there here, y equal to c into x. So there is no d. Therefore, there is no need of that. Okay, d is 0. Now, divided by determinant of si minus a. First, we will see si minus a matrix and we will see the determinant of that. Okay, we will calculate that separately first. Now, what is si minus a? Si minus a matrix, which is nothing but yes, 0, 0, yes, because identity matrix order is 2 by 2, because A matrix order is also 2 by 2, minus 2, minus 3, 4, 2. So which is nothing but Si minus A matrix is Si minus A matrix is S plus 2 plus 3 minus 4 S minus 2. This is Si minus A matrix. And what is the determinant of that? Now, determinant of adjoint. First adjoint we will see. Adjoint of Si minus A matrix is diagonal element position is changing. S minus 2, S plus 2. Diagonal element position is changing and opposite diagonal element sign is changing. Minus 3, now this is plus. This is adjoint. And what about the determinant? Determinant of Si minus A is now A, B, C, D. AD minus BC. A, B, C, D. And determinant is AD minus BC. What is AD minus BC determinant? Now S minus 2 into S plus 2 AD minus BC 3 into minus 4, which is equal to 0. Determinant of Si minus A equal to 0. A plus B into A minus B. A square minus B square. Now 12 minus minus plus 12 equal to 0. Therefore, S square plus 8 equal to 0. 12 minus 4, 8. Okay. So now this is the adjoint and determinant and Si minus A matrix. So we can write here directly. Now which is nothing but, what is C? C matrix. This is A, B, C. So what is C? C is nothing but 1, 1 into adjoint of, what is adjoint of matrix? Is nothing but S minus 2 minus 3 4 S plus 2. Now B, what is B? B is nothing but 3 5 by determinant is, determinant of Si minus A is S square plus 8, which is equal to now this is 2 by 2 matrix. Now this is 2 by 1 matrix. 2 to cancel. Now therefore this is 2 by 1. Now 3s minus 6, 3s minus 6 minus 3 into 5, 15. Three s and 3 into 2, 6 and minus 3 into 5, minus 15. And this is the 4 into 3, 12 plus 5s plus 5 into 2, 10. So this is divided by S square plus 8. So finally the transfer function y of s by u of s, which is equal to 1 1 into 3s minus 21 and 5s plus 22 divided by S square plus 8. So this is further we can extend it. Now this is 1 by 2. This is 2 by 1. Now this is cancelled and only 1 by 1 matrix. Now only the 1 by 1 matrix, which is nothing but 3s minus 21 plus 5s plus 22 divided by s square plus 8. Therefore, finally, which is nothing but the state space model transfer function 8s plus 5 plus 3, 8s plus 1 by s square plus 8. Now this is the state space model transfer function. Now this is finished. This is the state space model transfer function. Now next, eigenvalues. You know eigenvalues. What is eigenvalues? The characteristic equation roots. What is the characteristic equation? The characteristic equation is determinant of Si minus A equal to 0. This is already calculated. What is the determinant of Si minus A equal to 0? This is the characteristic equation. Denominator polynomial. Denominator polynomial. S square plus 8 equal to 0. Therefore, S equal to plus or minus J root 8. S equal to plus or minus J root 8. Now, what are the eigenvalues? This is the eigenvalues. The eigenvalues are plus J root 8 and minus J root 8. These are the eigenvalues. The eigenvalues are plus J root 8 minus J root 8. Now the eigenvalues which lies, eigenvalues is nothing but similar to closed loop poles. So this is the question for eigenvalues. Eigenvalues are completed. State space model transfer function is completed and eigenvalue is completed and stability. Now the eigenvalues which is similar to closed loop poles which lies on imaginary axis. Therefore, now the state space model is marginally stable, conditionally. This is the state space model which is marginally stable. Now one more question is also asked in one GATE examination. Same, this is given and this state space model is said to be, like that the questions are given. This state space model is said to be, options are critically damped, overdamped, undamped, underdamped, like that the questions are given. So you can easily find, now this is the state space model, closed loop poles. The closed loop poles which lies on imaginary axis. If the closed loop poles which lies on imaginary axis, system is marginally stable, means damping factor zeta is 0, which means that this is undamped response, undamped system. Like that the questions are asked sometimes. Okay. So all the three questions, state space model transfer function, eigenvalues, stability, and which type of a system it is, a damped system or overdamped, underdamped, everything is available. Okay. Okay. Now this is the question number 1. Question number 1 means in that question you may ask transfer function, eigenvalues or stability. Okay. I will cover everything in this particular question. Okay. Now sir, is there any other question? Yes. Now what type of question? Now he may ask. Okay. Then we will find out. Now see here, this is the state equation dx of t by dt, which is equal to a into x of t plus b into u of t. This is state equation. This is the state equation, okay? Dx of t by dt, which is equal to a into x of t plus b into u of t. This is the state equation. Now see here. Now this state equation is having a solutions, okay? Now I just check one by one solution, okay? Now, homogeneous solution. Homogeneous solution means input free condition u of t equal to 0. Input free means u of t equals 0. U of t 0 means what is the equation? Dx of t by dt, which is equal to a into x of t. Am I right? No, homogeneous solution means input, you remove input, okay? So this is dx of t by dt equal to a into x of t. Now in this equation, now without initial condition, you can get one solution, almost same, okay? It's not a problem, okay? Without initial condition, and this is with initial condition. Listen carefully, okay? Input free, first you remove input, means this is only the equation dx of t by dt. If you remove the input, now this is dx of t by dt, which is equal to a into x of t. Now this is the input free condition. Now remove the input, then this is the input free condition. Again there are two conditions, without initial condition, with initial condition. So without initial condition means x of 0 is 0. Don't take x of 0. So with initial condition means x of 0 is existing. X of 0 is available, x of 0 is not available here. Okay. So this is one set of solution of state equation. Okay. Now this is the, I am talking about solutions of state equation. This is the story of solution of state equation. And there is another thing here. Now this state equation, now is another solution is non-homogeneous solution. Non-homogeneous solution. The non-homogeneous solution means u of t should be present. U of t is not equal to 0. Okay. So one is homogeneous solution, now without initial condition and with initial condition. So another one is non-homogeneous solution. Now u of t is not equal to 0. Now this non-homogeneous solution is having two parts. One is 0 input response, another one is 0 state response. Okay. 0 input response. Now this 0 input response is due to initial condition. Now this is 0 state response. This is due to input. So the total x of t, solution is nothing but 0 input response plus 0 state response. The total x of t, now x of t is nothing but now 0 input response plus 0 state response. Okay. Now the total response of x of t is nothing but 0 input response plus 0 state response. No. Now we will see all these things, all the possibilities we will see. So general input is existing, therefore this is the general and exact solution. Okay. Now we'll see. One by one we will see. Now this is state equation, solutions of state equation. This is the state equation. So in this state equation, now first we'll see homogeneous condition, homogeneous solution. Homogeneous solution means first you want to remove u of t equal to 0. Homogeneous solution means u of t equal to 0. U of t equal to 0. So if this u of t equal to 0, dx of t by dt, which is equal to a into x of t plus b is 0. Then there is no u of t is 0. So this is, let us take this is a number 1 equation. Okay. Now apply Laplace transformation. Now apply Laplace transformation. Now s into x of s, which is equal to a into x of s. I am not taking any initial conditions. Okay. So or you can take, okay, you can take, not a problem. X of s into x of s minus x of 0, which is equal to a into x of s. Then take x of s as a common, which means that si minus a, which is equal to x of 0. What is x of s? X of s, which is equal to, this is a matrix, si minus a matrix inverse into x of 0. Apply inverse Laplace transformation. If you apply inverse Laplace transformation of x of s is x of t, which is equal to inverse Laplace transformation of si minus a matrix inverse into x of 0. Okay. So then again I'll take the same equation, dx of t by dt, which is equal to a into x of t. This is equation 1. Now can I do the solution of first order differential equation with constant quotient? Complementary solution, d into x of t, which is equal to a into x of t. So if you take d minus a into x of t equal to 0, now this right hand side is equal to 0, therefore only complementary solution. So what is the root? Root equal to real root. This is the root. So only a real root and a single root. What is the solution now? X of t, which is equal to some constant c1 into e power plus a into t. Okay. c1 into e power plus a into t. Now this is x of t. See here, this is x of t, solution of the same equation 1. This is also x of t, solution of the equation 1. So can I compare these two? Can I compare? Yes. If you compare e power at, which is equal to inverse Laplace transformation of si minus a matrix inverse. Si minus a matrix and its inverse, and again the total inverse of that. Now this is a function of time, therefore you may represent this as phi of t. Now this is the solution of state equation under homogeneous condition, means input free condition. Now this solution is named as state transition matrix. This is called as state transition. This is the state transition matrix. This is the solution of state equation, which is called as state transition matrix. Okay, note down. Okay. Now this is the solution of state equation under homogeneous condition. Now this is nothing but state transition matrix. So one of the question maybe he is asking find state transition matrix. Then you just use that particular formula directly. Now let us take for example, if A equal to 1, 0, 1, 1, this is the A matrix which is given, and he is asking to find state transition matrix. Therefore this may be one question. Find state transition matrix. Let us take, this is question number 2. State transition matrix is a solution of state equation. Now that solution is nothing but under homogeneous condition. So what should you do? First Si minus A matrix and then inverse. First you find Si minus A. What is Si minus A matrix? This is Si minus A. But what is A here? A here is 1, 0, 1, 1. Si minus A. So which is nothing but S minus 1, 0 minus 0, 0, 0 minus 1, minus 1, S minus 1. This is Si minus A matrix. Now, adjoint of Si minus A. What is adjoint? Adjoint is nothing but diagonal element position is changing and opposite diagonal element sign is changing. S minus 1, S minus 1. A and D positions are interchanged and opposite diagonal element sign is changing. Therefore, this is adjoint. And what is the determinant of this? Determinant of this is AD minus BC. Determinant of this is S minus 1 into S plus 1. AD minus BC 0 into plus 1. So the determinant of Si minus A matrix is S minus 1 whole square. Then what is this? What is the state transition matrix finally? The state transition matrix, which is nothing but pi of t, which is nothing but e power at, which is nothing but now inverse Laplace transformation of, okay, now first we'll see Si minus A matrix inverse. Now Si minus A matrix inverse is nothing but, what is Si minus A matrix inverse? Si minus A matrix inverse is nothing but adjoint of Si minus A by determinant of Si minus A. So adjoint is S minus 1 0 plus 1 S minus 1 by determinant is S minus 1 whole square. Therefore Si minus A matrix inverse is Si minus A matrix inverse is nothing but S minus 1 cancel, 1 by S minus 1 whole square 0, 1 by S minus 1 whole square 1 by S minus 1. This is the Si minus A matrix. Now this is the matrix inverse and inverse Laplace transformation of that. Now the inverse Laplace transformation of that Si minus A matrix inverse is available. Whose inverse Laplace transformation is? What is inverse Laplace transformation of 1 by S minus 1? The inverse Laplace transformation of 1 by S minus 1 is e power t. Now 0. Now 1 by S square t into e power t. Now e power t. Now this is the inverse Laplace transformation of Si minus A matrix inverse. This is the inverse Laplace transformation of Si minus matrix inverse. Now this is nothing but a state transition matrix. This is nothing but the state transition matrix. Clear or not? Not on. Now this is the state transition matrix. Which is the solution of state equation under homogeneous condition. Now you just see here. Now this is pi of t. So now students here, this is pi of t. What is pi of 0? Pi of 0, which is nothing but, see, substitute t equal to 0, e power 0, 1, 0, 0, 1. Now which is nothing but 1, 0, 0, 1, which is nothing but identity matrix. Pi of 0 is nothing but an identity matrix. Next, pi of t whole power k, we can write as pi of kt. Yes, pi power minus 1 of t, which is nothing but pi of minus t, and pi of t1 plus t2, which is, we can write it as pi of t1 into pi of t2. Yes. Now this is nothing but properties of state transition matrix. Note down.